Today, we're going to take a look at the last function in our series for this unit. It's going to be the rational function, which you guys spent some time looking at the Desmos activity. Right, so I hope that gives you a good idea of what the function looks like and how it behaves. Again, if you have any questions regarding the rational function, make sure you write down a note somewhere in your notebook that I can help you answer when we're able to discuss it. Okay, so let's get started here with the general form. So the general form is going to look like a over x minus h plus k, right, where k is added to the outside of the fraction. Okay, a, h, and k are still the same pieces of the function that we've had for absolute value and square root, right? So a still controls direction and whether it stretches or compresses. It also, H controls are shifting to the left and right, and K controls any shifts up or down. Okay, so let's go ahead and get started here with um, finding the vertical and the horizontal asymptotes of the rational function. Those are essentially the building blocks because it helps you identify where the curves are going to be bounded between. Okay, so every rational function will have two asymptotes. It will have a vertical asymptote. Actually, let's do a different color. So vertical asymptote and a horizontal asymptote. All right. So a vertical asymptote is just a vertical line that the graph cannot touch. Okay, so an asymptote in general is a line that the graph will approach but never touch. Okay, so you've seen asymptotes with exponential functions and now with rational functions. All right, so in order to find the vertical asymptote, it's quite simple. What we do is that we take the denominator, which in this case is x minus h, and we set that equal to 0. Okay, so it looks like this, x minus h, and we set it equal to 0. Okay, so make a little note here, set denominator equal to 0. Okay. All right, so when you solve, right, in this case, we would just add h to both sides, so you'd end up with x equals h. Then that tells you that there will be a vertical line where x is equal to h. And remember that h will eventually become a number, right? So we won't be dealing with two variables. It could be like x equals 1, x equals 5, whatever h happens to be, that's where the vertical line will go. Okay. Now the horizontal asymptote is very easy. It's actually less work than the vertical asymptote. The horizontal asymptote is going to be a horizontal line, right, that the function cannot cross. Okay, and the way that we look for it is just by finding k. All right, so you're just going to create a horizontal line that's going to say y is equal to, in this case, k. All right, so you'll have two separate asymptotes. All right, so just make a quick note here that a vertical asymptote is going to be a vertical dashed line at x equal to h. And the horizontal asymptote will be a horizontal line, or dash line, I'm sorry, at y equals k. All right. So it looks, I know it looks a little confusing because we were dealing with x and x, h, y, k, right? But once we replace h and k with numbers, then it should make a little bit more sense. Okay. All right. Now the vertical and the horizontal asymptote also help us find the domain and the range for this function. Okay. So rational functions have certain restrictions, and that's because if you look at what the rational function is, right, take a look at this piece right here, that's a fraction. Okay, and you should know something about fractions, that fractions are not allowed to have 0 in the denominator. Because if you do, then that converts it into an undefined number. Okay, it's not no solution, it's just undefined. All right, so it's a different vocabulary that we're using. Whenever you get undefined numbers, then that tells you that there's a problem. All right, so the reason why we have vertical and horizontal asymptotes is because there's certain numbers that the function is not allowed to have as a domain, or there are certain numbers that are not allowed to be part of the inputs, and because there's certain numbers that can be inputs, that results in a certain number that cannot be an output. All right, so in order to find the domain here, domain again, remember, is related to your vertical asymptote. So if I'm looking for domain of this function, okay, it's very similar to what we did to solve for the vertical asymptote, except the difference is that we don't want x to be that particular number which generates the vertical asymptote. Okay, so what I'm trying to say is this, that the domain is going to be a set. All right, so here I'm using set notation, which is a little different from interval notation because it's actually easier to write it in set notation. Because it's every number, we're just going to exclude one of them because only one number is what's going to cause the problem. All right, so what I would say here is that my domain is x, is the set of all x's such that x does not equal h. Okay, I don't want x to be equal to h because if it is, then essentially it would subtract and become 0, and then I would end up with a 0 in the denominator, which is what I don't want. Okay, so another way to say this is to say all real numbers except h. Okay, I'm going to show you also the interval notation of that just in case. Okay, it's not as easy to write. Okay, however, I just want to show you. So interval notation would be, if I'm including every real number except for h, then essentially I'm starting from negative infinity, right? All of the numbers down towards negative infinity. Then when I get to h, I'm going to exclude it. Okay, I'm going to exclude h, so I put a parenthesis around it. But I also want the numbers that are going to be bigger than h. So then I need to union it with starting with h again, but not including it, all the way up to infinity. So really what this interval says is that all the way from negative infinity to infinity, but notice that the only number that's not included is h, right? We didn't include it in either interval, right? There's parentheses for both. Okay, so that's another way to write it, and that's more interval notation. All right, now let's talk range. And with range, it's the same idea. So in this case, we're looking at all of the possible y values, all y values, the set of all y values, such that y does not equal k. Okay, so there's a little bit of a pattern here. The value for h is what becomes your vertical asymptote, but that's the one number that cannot be part of the domain. For your range, k is going to be where you draw your horizontal asymptote, but it's the one number that's not allowed to be part of the range. Okay, so then for range here with this set, right, here's our set notation. Then the way we can say this is all real numbers. The range is all real numbers except k. All right, and then we would write that interval notation very similarly to the one that we got for domain. So it's from negative infinity to k, not including k, but I want all the numbers bigger than k. So then from k to infinity, once again, not including k. All right, and then finally, we'll discuss what the shape of this function is going to look like. All right, so the shape has a particular name. Just like with quadratics, we had u-shapes, which their formal name is parabola. With rational functions, the shape of the function is called hyperbola. Okay, hyperbola. Kind of similar to the name parabola, except there's not much of a similarity besides the fact that the parabola is a curve and hyperbola is as well. Okay, so hyperbola, it has two curves that don't touch. Okay, they don't intersect. All right. So it's a lot of information just to get us started, but I want to lay it out because I'm going to follow this process, right? I'm going to start with the function. I'm going to identify vertical and horizontal asymptotes. That's going to help me create a building block, right? It gives me a foundation where I know that the graphs are going to be bounded between. Then I'm going to look to see, okay, what is within my domain, what's not, what's within my range and what's not. And then we can move forward from there. All right, so let's go ahead and start just like always with the parent function. So move on over to the other side. Okay, for this page, you don't need to try to squeeze in more than just 2 boxes. So I recommend you just split it down the middle and then you leave enough space because I want to make sure that it's not too tight. There's a lot of information. All right, so starting with the parent function, we have f of x is equal to 1 over x. Okay, and just like always, right, it's hard to see what h and k are when the function is written like this. Okay, so I'm going to rewrite it as 1 over x minus 0 and then plus 0. Okay, so notice that nothing has really changed. If you subtract 0, if you subtract nothing from the denominator, you didn't change it. And if you add nothing to the outside of that fraction, you haven't changed it either. Okay, but now what we can say is, well, I know what my h is, and I know what my k is. Right, so now we can go ahead and start by identifying both the vertical asymptote and then our horizontal asymptote. Okay, so let's go back to the original here, or actually we can work with this one right here. Okay, notice that in order to find vertical asymptote, we are going to set denominator, the entire denominator, equal to 0. So we get x minus 0 equals 0. Well, in that case, if I add 0 to the other side, I still have x equals 0. So that means I have a vertical asymptote VA at x equals 0. Right? So I'll need to draw a dashed line going straight up and down at x equals 0. For the horizontal asymptote, this one's easy. We're just going to set it equal to k. Right? That's our k there. So then y is equal to 0. Okay? Or y equals k. Right? Where k is 0. All right. So there I have my two asymptotes. Okay? Even before I graph, I already know what my domain is going to be. Right? Because I know that I'm trying to exclude a certain number that's going to cause a problem with this particular function. If you look at this function right here, 1 over x, there is a particular number that cannot be plugged in for x. Okay, what is that number? That number is 0. Okay, because if you plug in 0 for x, guess what? 1 over 0 is not defined. Check it in your calculator and you're going to get a syntax error. Okay, so I know that that is the value that cannot exist in my domain. It also happens to be my vertical asymptote. Right? The vertical asymptote, remember, is the line that the graph cannot touch. So there's a reason why the graph will get close to it but not touch it, because I can't actually have a y value when I plug in 0 for x, okay, because I'm going to get undefined. Okay, so let me go ahead and write out this domain. The domain, remember, in general form is, or in set notation, is going to be all values of x such that x does not equal, we do not want x to equal 0, okay, because it's going to cause some issues. All right. For my range, it's going to be the set of all y values such that y does not equal 0, okay? So 0 is going to be the one input that I cannot have, and 0 is the one output that my function will never be, okay? It will never be 0, okay? So now let's go ahead, let's move on and try to graph this. All right, so let's plot this. All right. So since I know I have a vertical asymptote at x equals 0, I'm going to draw that first. Okay, so starting here, when x is 0, that's a vertical line. Okay, and I can label this as VA, x equals 0 for vertical asymptote. And then going across here at y equals 0, there's my horizontal asymptote, y equals 0. Okay. All right. So those are my boundaries, right? Those are the two lines that my graph will not be able to touch. Now I still need I need some points. I need something to be able to sketch a graph so I have an idea of how this looks. Okay, so let's make a t-table here. I'm going to make a t-table off to the side. Okay. And I want to have enough space for about 9 values. I know it's a lot. I know 9 values is a lot, but just to start off, just so we get an idea of how this is going to look like. Okay, so I'm going to start with utilizing 3 numbers to the left of 0. Okay, 0 is kind of like my baseline. It's my starting value essentially because I know that I cannot use 0. So I need numbers that are going to be to the left of 0 and then to the right of 0. Okay, so I'm actually going to place 0 in here somewhere. 1, 2, 3, 4. Okay, I'm going to put it right in the middle. Okay, so then now I can pick some points to the left. We're going to go with -3, -2, -1, and actually -1/2. I want to see how the function behaves when I plug in another fraction for x. Okay. All right. And then on the other side of 0, we're going to choose the exact same values. 1/2, 1, 2, and 3. Okay. All right. So let's start here with x is equal to 0, right? Pretend that we plug that into the function 1 over 0. Well, we've already discussed what is going to happen here. This is going to give us undefined. Okay, it's just not possible. Okay, now let's do the rest with the rest of the values. If I take -3 and I plug it in for x, then that's just going to convert the fraction into 1 over -3. Then if I take -2, it's going to be -1 over 2. I plug in -1. Well, -1 over 1 is just -1. And then I can take 1 divided by -1/2. Okay, for this piece, I'm going to do a little bit of scratch work on the side just to remind you of what it looks like when you take a fraction divided by a fraction. Okay, so here what we essentially have is 1 divided by -1/2. Now, you've learned that if you're dividing by a fraction, then you're supposed to multiply by reciprocal. So it becomes 1 times -2 over 1. Okay, well now essentially what we're just doing is just taking 1 times -2, which is -2. Okay, so this becomes -2. All right, now let's do the same thing for 1/2. Okay, so I have 1 divided by 1/2. Notice how it's essentially the same thing, except we don't have the sign. So this becomes 1 times 2 over 1, and 1 times 2 is just 2. So we get 2. Okay, if I plug in 1, that's 1 over 1, that's 1. If I plug in 2, I get 1/2. If I plug in 3, I get 1/3. Okay? All right, so there we have plenty of points. Okay, I needed this many because I am essentially creating 2 different curves, one to the left of 0 and one to the right. Okay, if you don't have enough points, you're not going to get any information for the curve that exists on the right side, right? So that's why I'm using so many. All right, so starting with -3, 1, 2, 3, we go down 1/3. Okay, so you're not even going to go halfway, you're going to go less than halfway. Okay, so let's go somewhere about here. All right. Then -2, -1/2. Okay, so that one we can go halfway. -1, -1, that's here. And then -1/2 and -2. Okay, so you see, I can see the curves start to develop. Now, do you see how the points, right, they're getting closer to these lines, but what we know about the line is that the curve cannot touch the line. All right, so when you draw this, okay, I can get really close to that asymptote, but I can't actually touch it. Okay, it's not going to cross. Right, so my line should look like that, right? And that should look somewhat familiar based on the Desmos activity. Okay, now let's plot the points that are on the right side. So we go we go +1/2 up to, then we go 1, 1, then we go 2, 1/2, and then we go 3, 1/3. Okay, so same thing, right? You have a curve. that gets close to the x-axis and then a curve that gets close to the y-axis, but they don't actually touch. Okay, and there's your function. There's your rational function. Okay, notice everything that's been labeled. Both of the asymptotes, horizontal asymptote and vertical asymptote, right? We've defined the domain. We've defined the range, right? We did it even without even having to graph it, right? But you can see here now, as I'm going from left to right, look at the function. It's going all the way to negative infinity, and then it's moving to the right. But as it moves to the right, it starts going down. It gets really close to that vertical asymptote, but it cannot cross it. So then because it can't cross it, it can't touch it, then we have to exclude 0 as part of the domain. Then it picks up on the other side, and you see it right here, right? It picks up right here after it's jumped, and then it keeps going all the way to positive infinity. So then my domain is allowed to be every number except for 0, and then the same thing happens for the range, right? Notice that the function starts from the bottom down here, and it's moving up, right? So from negative infinity, it's coming up, but it can't reach 0. It can't actually touch it. It gets really close to it, and then we see it show up again on the other side of 0, and then it moves up. Right, so when it moves up, then we know it's moving up towards positive infinity. Okay, all right. Let's move on then. So that's our parent function. Now we have an idea of what that's going to look like, and we can then make some observations on the transformations that would occur on other functions. Okay, so let's go ahead and move over to the next page. I recommend you go over to the next page. Next page, make 4 boxes. We're going to do the work on the left, and then we'll just do the graph on the right. Okay, so let's go ahead and do that. Okay, so next example, next function, we have f of x is equal to 1 over x plus 3 and then minus 2 on the outside. Okay, so before we begin, let's just talk about the transformations that we expect here. Okay, so we know that here is where h would have been, right? So that's our opposite. So instead of shifting 3 to the right, we're going to be doing a horizontal shift, 3 units left. Okay, and then this is our k, right? So we keep that. So that tells us we have a vertical shift 2 units up. I'm sorry, not 2 units up, 2 units down. All right. Now, whenever you shift a function, a rational function, you're shifting the asymptotes with it. Okay, so in this case, if I'm shifting the whole function 3 units to the left, well then that asymptote that used to be here at 0 is also going to get shifted 3 units left. Okay, this horizontal asymptote that was at 0 is not going to get shifted 2 units down. Okay, so I hope that makes sense, that when the function moves, the horizontal and the vertical asymptotes move with it. Okay, so we're going to have different asymptotes for this graph. Okay, so if I'm looking for vertical asymptote here, what are we going to set equal to 0? Okay, we're going to set this denominator, the whole denominator, equal to 0 to help us find that horizontal asymptote. So x plus 3 equals 0. Therefore, we get a vertical asymptote at x equals negative 3. Right, that makes sense because we were going to shift everything 3 units left. Well, if I shift it left, then I'm going to end up at negative 3. Okay, if I'm looking for a horizontal asymptote, this is even easier. I know that my k is negative 2. So then I'm just going to write a function here that y is equal to negative 2. Okay. All right. So from here, right, we can also go ahead and just state our domain. We know that our domain our domain is going to be all x such that x does not equal. What do we not want it to equal? Is -3, right? Imagine that you were to plug in -3 here for x. What would happen? You'd get -3 plus 3, 1 over -3 plus 3, which ends up being 1 over 0. Boom, you get undefined, right? So that's why we don't want x to be -3, right? That's why we're excluding it from the set, all right? And then same thing for the range. In this case, the one value that we're not allowed to be is -2. That's the one output that we're going to exclude from the range. So all y values such that y does not equal -2. Okay, so domain's all set. And so are our vertical and horizontal asymptotes. Okay, so I'm going to start drawing that foundation. Okay, so on the xy plane, I'm going to draw vertical and horizontal asymptotes first. All right, so let's do horizontal or vertical asymptote in blue. So at -3, 1, 2, 3, -3 here, there will be a vertical asymptote there. Okay, so we can label this VA, vertical asymptote, x equals -3. And then I have a horizontal asymptote at -2. So at -2, right here, we can draw a horizontal line there. So this is HA at y equals -2. All right, so from here, before I do anything else, I need a t-table because I need to plot some points so that I can draw the rest of the curves. Okay, so let's go back to the left side of your paper and let's make a t-table there. All right, I'm gonna go horizontal this time. Actually, no, I'm gonna keep it vertical. I'm gonna stay consistent. So here's x, here's y. Okay, I know that the value that causes problems is -3. Okay, so I'm gonna go halfway down. I'm gonna leave enough spaces for 3 numbers. So 1, 2, 3, and then I'll use -3 as kind of like my middle. Okay, I know that when I plug in -3, that's the problematic one, right? When I plug it in, that's what ends up giving me 0 in the denominator. So I know that when I plug in -3, I get undefined. Okay, so I'm gonna pick some numbers here to the left of -3. So let's go with -4, -5, and -6. Okay, and then I'll pick numbers on the other side, so we'll go with -2, -1, and 0. Okay. All right. With rational functions, I highly encourage you to use a calculator. Okay, I don't want you to spend too much time trying to clean up these fractions, or I don't want you making too many mistakes on them. I just want you to find the correct output, use it, and then graph it well. Okay, so let's start with -6 here. When I plug in -6, I'm going to have, let me zoom in actually. Our original function was 1 over x plus 3 minus 2. Okay, so I'm going to have 1 over -6 plus 3 and then minus 2. Okay, so first I need to clean up that denominator there. Okay, imagine like this is in parentheses, right? You have to clean that up first. So then you have 1 over, that's going to end up being -3 and then minus 2. Okay, so use a calculator to help you on this piece. This is eventually going to end up being -7 over 3, which is approximately -2 and 1/3. Okay, so you have an idea of where that's at, -2 and 1/3. Let's do the same with -5. We get 1 over -5 plus 3 and then minus 2. This equals 1 over -2 minus 2. So eventually we get -5 over 2. And that's approximately equal to -2 and 1/2. Okay. Now when I plug in -4, 1 over -4 plus 3 minus 2, that's going to end up giving us 1 over negative 1 minus 2. Well, that becomes negative 1 minus 2, which is equal to negative 3. Okay. All right, now let's go towards the other side. 1 over negative 2 plus 3 minus 2. That's going to give us 1 over 1 minus 2, which is 1 minus 2, which gives us negative 1. 1 over negative 1 plus 3 minus 2. That's going to be 1 over 2 minus 2, which is negative 3 over 2, which is again negative 1 and 1/2, okay, or negative 1.5. And then if I plug in 0, that's going to be 1 over 0 plus 3 minus 2, which is equal to 1 over 3 minus 2, which ends up giving us negative 5 over 3, okay, which is going to be negative 1 and 2/3. Okay. Let me double check my math here real quick. Let's see. This will be, yep, that looks good. All right, so now we're ready to graph, okay? So let's move over here. So at negative 6, I have negative 2 and 1/3, right? So I got to go 6 to the left, 1, 2, 3, 4, 5, 6, and then down negative 1, 2, and then 1/3, right? So a little bit lower than the negative 2, right? So I have a point right there. Then we go to negative 5, 1, 2, 3, 4, 5, and then down negative 2.5, so a little bit beyond where we plotted the 1/3. Okay, and then at negative 4, we can go down to negative 3, okay, which would be right here. Okay, so do you notice there is a slight differentiation between those points, right? But we need to understand that that means that the curve is going to look like this, right? It's approaching the horizontal asymptote, then it starts to pull away, and then as it gets closer to the vertical asymptote, it starts to run alongside it. Okay, that's essentially what our graph is going to look like. Okay, if I want to get a more specific one, then I would have had to use something smaller, and in between negative 4 and negative 3, I would have had to have used like negative 3.5. Okay, so that's why those 3 points, you have to understand what the picture looks like. Okay, otherwise we need to use more points. Okay, and that's what I'm trying to avoid. Okay, so we can do this, we can sketch this quicker. All right, on the other side now, okay, there's a little bit of a pattern, right? If I have the graph down here, right, in the lower left side, then my other graph is going to be somewhere up here in the upper right side. Okay, so at negative 2, right, using these points right here, negative 2, go down negative 1, I have a point there. Actually, let's go black. Negative 2, go down 1. At negative 1, negative 1 and 1/2. Okay, so down 1 and then half of that. And then at 0, negative 1 and then 2/3. Okay, so almost touching that asymptote line. Okay, all right. So then it almost looks like the same shape, kind of reflected in a way, right? And the function is going to be coming down this direction. So there's our function right there. Okay. And again, if I wanted to get another point, right, I would have had to have found something probably right in here, in between negative 3 and negative 2. I would have had to have plugged in something else to give me a little bit more specific as to how high to go on the function right here, right? Like if I would have chosen negative 2.5, that would have given me a little bit more details and specifics on the function. Okay, but if you can understand what the shape is going to look like, then you don't really need 4 points. You really only need about 3 on each side. Okay, all right. Let's move on now to the next one. Again, if you have any questions, try to write them down, make a note somewhere about what you didn't really understand so that I can try to answer them in person. Okay, let's move on here. All right, next function.